In this video, we'll discuss how normalizing flows can be used for density estimation and computing expectations with respect to complex distributions. The key idea behind normalizing flows is to construct complex distributions from simple ones via a flow of successive invertible transformations. And the key ingredient for normalizing flows is the change of variables trick. So let's have a look at this first. The key idea behind the change of variables is that we transform a random variable x into a random variable z using an invertible transformation phi while keeping track of the change in distribution. The distribution p of x induces a distribution p of z via phi, and the distribution p of z induces a distribution p of x via phi inverse. To understand how a change of variables works, we need to have a look at the Jacobian determinant. Assume we want to transform x into z via a transformation phi, then the determinant of the Jacobian d phi dx tells us how much dx is stretched into dz. Keeping in mind that the Jacobian determinant is a scaling factor between two different domains, here's how the change of variables tricks works. By definition, the integral of a density over the entire domain is 1. That's true for both px and pz. If we now transform a random variable x into z via phi, then we know that the Jacobian determinant tells us, loosely speaking, how much bigger z is than x. And if we want to compute pz from px and the transformation, we need to divide by the Jacobian determinant to make pz a valid density. The change of variables tricks allows us to express a target distribution pz in terms of a known distribution px and the Jacobian determinant of an invertible mapping phi. There's no need to invert phi explicitly because the determinant of an inverse is 1 divided by the determinant of the forward mapping. The change of variables trick therefore allows us to generate expressive distributions pz starting with a simple base distribution px and a flexible invertible transformation phi. The change of variables tricks has some interesting applications. For example, it's useful in numerical integration to turn indefinite integrals into definite ones. It's also central to the idea of normalizing flows, neural ODEs, implicit generative models, and likelihood-free inference. So now let's go back to the normalizing flows. As we said earlier, the key idea is to construct complex distributions from simple distributions via a flow of successive invertible transformations. Let's have a look at how we can construct these complex distributions. Assume we have a random variable z0 that has a simple distribution, for example, a standard normal. We write down an iterative scheme to compute successive random variables zk from zk minus 1 via an invertible deterministic transformation fk. That means zk is a function of zk minus 1. We do this a few times and we set observed data to correspond to the random variable at the end of the chain of transformations. So x equals z capital K. That means we know the two endpoints of the chain, the base distribution p0 and the data at the end of the chain. If we find good parameters of these invertible transformations fk, then we have a prescription of how to generate data from a simple base distribution. Let's now have a closer look at the distribution of the data. We can compute the data distribution by repeated application of the change of variables trick so that px is the base distribution times the product of 1 over the absolute value of the Jacobian determinants. Similarly, we can compute the entropy, which just sums up the log determinants of the Jacobians plus the log of the base distribution. Let's have a look at an example. We start off with a standard normal distribution and repeatedly apply a planar flow to this base distribution. The planar flow has a resonant structure. It takes the previous random variable and adds a nonlinear transformation to it. Basically, this nonlinear transformation is a linear model squashed through a sigmoid. After one planar flow, we see that we can already express correlations. That means the density here is tilted. And then we go on to 2 planar flows and 3, 7, and 12. we see that we transformed the simple standard normal distribution into a very complicated and multimodal distribution. Now let's get back to computing expectations with normalizing flows. Assume we have a loss function L and we want to compute an expected loss with respect to P of x. We know that P of x equals the distribution at the end of the normalizing flow, which we obtained by deterministic transformations of a base distribution. That means the expected loss with respect to P of x can be written as the expected loss of a transformed random variable with respect to the base distribution. And that also means we do not need to know what P of x actually is in order to compute the expected value. To compute the expectation, we sample from our base distribution and push the sample forward through the sequence of deterministic transformations and obtain a valid sample from P of x. We can then repeat this procedure and use a Monte Carlo estimator to get the expected loss we were interested in. There are some computational considerations that we have to be aware of in practice. Computing the log determinant of the Jacobian is computationally expensive in general. But if the Jacobian has a special structure, for example, it's diagonal or triangular, we can compute the log determinant in linear time. To get a triangular structure, we need to ensure that some partial derivatives in the Jacobian are zero, specifically these ones up here. That means all partial derivatives of the dth dimension of zk with respect to dimensions greater than d of zk minus 1 need to be zero. If that holds, we get the triangular form of the Jacobian, and the determinant of that Jacobian is then just the product of the diagonal elements. Autoregressive flows implement exactly this. At a high level, the dth dimension of zk only depends on dimensions 1 to d of zk minus 1. There are many variants of autoregressive flows, for example, nice inverse autoregressive flows, real NVP, masked autoregressive flows, glow, neural autoregressive flows, spline flows, and so on. Normalizing flows are used in many applications, for example, in variational inference, in deep generative models, graph neural networks, and parallel wavenet. We can also think of the normalizing flow that we discussed here as a discrete time dynamical system because we write zk as a function of zk minus 1. But there are also extensions to continuous time dynamical systems or continuous flows, and these ideas are being used in neural ODEs or to define flows on manifolds. To summarize, normalizing flows are a constructive way to generate rich distributions. The key idea is to transform a simple base distribution using a flow of successive invertible transformations. The key ingredient here is the change of variables trick that allows us to do this. Jacobians can be computed efficiently if the transformations are defined appropriately. Normalizing flows can be used for data generation and as an inference mechanism.